I can see that I'm going to get exactly one descent. Right? Here I have a descent between 1 and 2, 2 and 3, 3 and 4, 4 and 5. So these should contribute q to the weight of 1, q to the weight of 2, q to the weight of 3, and q to the weight of 4. And now I look up here and I see that 3 of my weights are 2 and 1 of my weights is 1. But when I look at tableau here, I also have 2 tableaux with just 1 descent. So this tableau has just a descent at 2, and this tableau has just a descent at 3. So altogether, these guys contribute 3q squared q, which means that these two should either contribute 2q squared or a q squared plus q to the 1, right? Because all of my weights are either 1 or 2, and there's only 1. But that doesn't happen. I only have 1 q squared, and I don't have any q's. So this whole idea, any weight system you can think of, is immediately ruled out by this example. And more than that, even if I didn't just try to sum up the descents individually, but looked at the whole descent set and said, well, there's some statistic per descent set, this doesn't work because this tableau and this tableau have literally the same descent set, and so does that one and that one. So MAJ may be possible to generalize, but sort of the natural first guesses don't work. But we have another hope. Not to fear. So just as with words, we have another statistic on Tableau which is equidistributed with MAJ, and that's called inv. And it is also looking into that Tableau, saying that 2 cells are making an inversion and then adding 1 to the statistic for each of those. So. And this inversion statistic was introduced by Haglund and Stevens in 2006. But it's very complicated. I warn you before I start. So, the idea to start with is that we want to look at when we have a small number and a big number occurring in the tableau and look at their arrangement geometrically. So if the small number is sort of below and to the right of the big number, then I want to say that this is definitely an inversion. For reasons you can justify thinking about RSK or something else. And if the small number is above and to the left, I want to say this is definitely not an inversion. But when they're kind of southwest of the big number, then it's not clear whether or not you want this to count as inversion. And if you just count these, you'll get sort of too small of a statistic, and if you count both of these, you get too big of a statistic. So we need to do something in between. And so the idea of Haglund and Stevens is that you're going to draw a path through the tableau, and that's going to separate these cells into sort of the good category and the bad category. So what does this look like? So let's look at this 8 here. You should definitely make an inversion with the 2, 5, 6, and 7. You should definitely not make an inversion with the 4, but for these two we don't know. And so I'm going to draw a path which starts here at the bottom left corner of my big number, and then it sort of moves in the direction of big numbers. So I compare the 4 and the 6. The 6 is bigger, so I move down. Maybe I use color now. The 6 is bigger, so I move down 1 step. And then I compare the 3 and the 2. The 3 is bigger, so I move to the right. And then I compare the 1 with nothing, and 1 is better than nothing. So I move down. Okay. So this path says that yes, 8 should make an inversion with 1, but it should not make an inversion with 3. So it separates this ambiguous region here into 2 pieces, and that's going to tell me, do I have an inversion or do I not? So this would be nice. This would be a nice statistic, but that's not the end of the story. I have to do something else before I can look at the next number. So I always do this for the biggest number, and then I do a Fawada type cycling before I move on to the next number and the next number. Okay, so next we cycle. Okay, so I want to look at when, whatever my path looks like, the 1 is on the same side as some number I, and then the next few numbers, however many of them there are on the opposite side before coming back over to this side. Right, so this is my thing that I'm going to cycle. A number alone, and then the next bunch of numbers together on the opposite side. And there's only one way to cycle so that it actually stays being a tableau in general, but instead of the small one being by himself, now the big one is going to be by himself. So I'm going to look for all of the blocks like this and cycle them all simultaneously, and then move on and draw another inversion path. So this is what we started with. And here's my path. So what are the blocks looking like? Well, the 1 and the 2 are on the same side, so the 1 is in sort of a loner block, and he doesn't get cycled. But then the 2 is opposite from the 3 and the 4, so these 3 numbers will be cycled. And then the 5, 6, and 7 are each alone on the same side as the 1. And once you get up to the number you had circled before, then you just copy everything verbatim. So 8 and above are fixed. And now I look at the next biggest number here, 7, and I repeat. So I compare 6 and 5, I compare 2 and 4, and then I compare 1 and nothing, and now I try to cycle again. Now 1 is above the path, so I want to look for loners above the path, and then a string of numbers on the opposite side. So 1 and 2 are fixed, and then 3, 4, 5 get cycled, and then 6 is fixed, and 7 and above are fixed. Repeat this. Oh, I'm still matching my notes. Yes, good. And now when I cycle with 5, I'm on the edge of the tableau. So my inversion path is going to say, don't cycle anything. And then I would look at the 4, and its inversion path would say, don't cycle anything. So I'm kind of done cycling at this point. Okay, so these are all my inversion paths. I did all my cycling, and the last step is to copy back to the original tableau. And count. So back in the original tableau, I draw each inversion path. all my inversion paths of anything that's not in the bottom row, because things in the bottom row can't attack anything. And I copied them back into the original tableau, and now I just count inversions under the path. So 8 makes inversions with 5 things. 7 makes inversion with 2 things. 6 makes inversions with 2 things, right? The 6 and the 7 are not making an inversion. 4 makes an inversion with these 3 smaller things, and 3 makes an inversion with these 2 smaller things, for a total of 14 inversions. So I say the statistic of this guy that we started with here is 14, and that's all the work I have to do every time I want to calculate one of these.
So this statistic is due to HS?
Yeah, Haglund and Stevens from 2006. And they proved not only is this equidistributed with MAJ, but they gave you the explicit bijection. So if you look at this last tableau that I got from cycling, his MAJ is going to equal 14 as well. So I have a descent between 3 and 4, between 4 and 5, and between 7 and 8, and those indeed add up to 14. So we have this explicit bijection between tableau with MAJ and tableau with IMS that's preserving the statistics. So I know these are equidistributed, and I can even see how it works. But it's hard to calculate, it's hard to work with. Too bad for us.
So what was the motivation for the
Well, trying to get at Macdonald polynomial things. So it's not just LLT polynomials that have this kind of Schur expansion thing where I know how many terms I want, but not the powers of Q. And so they knew we needed something that generalizes MAJ, and MAJ doesn't generalize so nicely. So kind of the same motivations as we have here, but in a different problem. Right, and this idea. So this is the thing, our new hope, since MAJ didn't work out, to try to generalize. So how am I going to interpret this? Well, as we saw from the motivation, there's something different going on when I have cells in this sort of configuration. So one thing to do is to look at hook shapes. So that means that I have a box here, and some number of boxes above it, and some number of boxes to the side, but nothing in here. So I can never have this configuration of a box and some other box southwest of it. So here there's sort of no cycling, no ambiguous inversions, everything is pretty, and I can ask the computer what kind of statistic works correctly here. And so based on the data, it looks like what I want to do is, so for hook shapes, I just want to count the non-ambiguous inversions exactly when they're attacking under the dick path. So if I have, say, this dick path, I can put the numbers on the diagonal just for easy reference. And I want to see what the statistic of this dick path should be for this hook shape. Okay, so since there's no weird configuration, everything is unambiguous. So I have an inversion between 1 and 2, and then I look over here and see if it's also an attacking inversion, and yes it is. I have an inversion between 5 and everything below it. But here 5 is only attacking 3 and 4. And then I have an inversion between 6 and everything below it, but only 5 and 6 are attacking. So the statistic of this shape should be 4. The computer data that this supports this idea for all hook shapes, where I don't have any ambiguous inversions. So the idea is to basically do something with inversion paths and cycling to get an inversion set, and then weed out the ones that aren't attacking in the dick path. Oh, this doesn't play. Another thing that the computer data supports is the idea that if I change the dict path by 1 square, my statistic should be the same or changed by 1, right? Because I'm only changing one attacking pair, either adding it or subtracting it. And this is backed up with computer data. For example, when I have this LLT polynomial, and I look at some particular coefficient, I get a polynomial. And if I just get rid of this 1 square, or rather add that square under the path, then what I want to see is all of my statistics staying the same or going up by 1. And that is what I see. I see that whatever tableau contributed 4 now contributes 5. Both of the tableaux that contributed 3 still contribute 3. And then these 2 tableaux contributing 2 split. One of them it goes up, one of them stays the same. So nobody had to increase by more than 1, nobody had to decrease. So it's all good, it's all copacetic. So we have good evidence that this kind of thing should work, but I also have good evidence that whatever works is very complicated. Partially because this inversion statistic is so complicated, but there's another bit of bad news I have to tell you guys, which is that I can't just have a set of inversions and then weed out by attacking. I have to do something more complicated. So I asked the computer, is there any set of inversions that I can correspond to these tableaux, and then just as I change the dict path, I weed them out by attacking? And already for the shape 3, 3, it didn't work. So already when n is 6 and the shape looks like this, there's some kind of internal contradictions. So I can't just say, oh, this tableau has this inversion set, and then cross off whichever ones aren't attacking. My procedure itself has to depend on the dict path, either the way that I draw the inversion paths or the way that I cycle. And so what Jim and I have mostly been experimenting with is changing the way that you cycle and keeping the inversion paths the same. And one reason for that is that these LLT polynomials have a nice product structure. What time is it? Oh no. I wanted to say so much more. So our main idea right now is to try to not cycle everything, but only cycle those numbers that are being attacked. So if my dict path, say, looks like this, so the 8 is only attacking 7 down to 3. It's not attacking 2 and 1. Then when I draw my inversion path in the usual way and look for cycling, I'm going to first fix these 2 cells that 8 doesn't attack. So I have this here. And I have my inversion path. And the first thing that I'm going to do is fix these 2 numbers that 8 doesn't attack, and then I'm going to start looking for cycles. So now I look and see what's on the same side of the path as the 3, and then cycle it. So the 3 is by itself, and then the 4, 5, 6, 7 get cycled. Etc. And this worked up to n equals 8. And at n equals 8, I'm checking over 1,400 paths against over 700 tableaux. So that's a million examples, and there's no way I would have noticed that this didn't work without the help of my computer. So it didn't work at 8.
Oh, okay.
It worked at everything up to 8, and then at 8 suddenly it breaks for just these central Schur coefficients.
So you have to tweak it in Macdonald.
We have to keep tweaking, yeah. So we have lots of other ideas. We're still hoping for more breakthroughs, and hopefully I can come back someday and tell you the true answer. Hopefully it'll be pretty.
Thank you very much.
So thank you guys.
Answer questions privately. Thank you, Jonas, for dinner.